Greetings all, this is lesson number 2 from chapter 17. I am recording this during a thunderstorm, so you might hear some thunder outside. Hopefully it will not knock the electricity out. I would like you to imagine that you're sitting on the steps down at the arch watching the Mississippi River go by. The amount of water, we'll use the letter I for current, that you see go by you, the amount of water, would be proportional to how much potential energy that water has. In other words, how steep is the channel? If the channel were steeper, the Mississippi River would be flowing faster on its way down to New Orleans. If the channel was shallower, or I should say not as steep, it would be traveling more slowly. Well, voltage is this potential energy per charge. The change in potential energy would be analogous to the change in height, implying a change in gravitational potential energy if we're talking about water. Now, in order to get rid of this proportional sign, we need to have a constant. So we could say that this change in potential energy equals some constant, and I'm going to use the letter R, times I. And letter R turns out to be the resistance to the flow of the water down the Mississippi River channel due to whatever obstructions might be in the way. Or in the case of electricity, it would be the resistance, not just in the wire, but in whatever devices are in the circuit, like light bulbs and buzzers and LED displays and things like that. This is Ohm's law. So resistance can be defined, that's what this triple line means, as the change in voltage, which is potential energy per charge, divided by the current, which is the amount of charge per period of time. So these volts per ampere are simplified simply by calling it an ohm. And since the letter ohm begins with an O, we're not going to abbreviate it with an O because it looks like a 0. So we're going to use the last letter of the Greek alphabet, omega. Maybe you remember in Revelation, Jesus is our Alpha and Omega, our beginning and our end. In terms of he's everything as far as our faith is concerned. Typically in your house, by the way, when you plug something in, most of the ordinary outlets are about 115, 120 volt sources. So the analogy of water going down a river helps here, even though there are exceptions to that analogy, or I should say limitations. It does help us to understand Ohm's law. Now, Ohm, by the way, was a high school teacher, so obviously he's a good guy. I don't know if you feel the same way, but I'd like to think that all your science teachers are making some kind of contribution, and hopefully a good one. Now, the resistance in many, many circuits, and certainly in circuits that use copper wires, for example, which are the most common, that resistance remains constant over a wide range of applied voltages or currents, meaning you can vary the voltage, you could vary the current, and Ohm's law would still apply. It is independent of how big the voltage is or how big the current is. You could always find the relationship between these three quantities. We would say that such a circuit is ohmic. Right down here. There we go. There are circuits, because of the materials that the circuit is made out of, that are non-ohmic, that don't show this linear relationship. We'll talk about that in a minute. But first of all, the symbol for a resistor generically is a zigzag line. And sometimes a resistor is just that. It's just a piece of material that's designed to use up some electrical energy in the circuit. It could be used, for example, to force the current to go to a different branch. It might use up some of the energy because the other thing that's in the circuit only requires a little bit of energy, and you don't want it to be too much. There's lots of reasons for using a pure resistor. Now, this picture right here shows you lots of different kinds of resistors, including variable resistors, which are called rheostats. In my house, the switch for the dining room lights has a rheostat. Forgot the O in there. And that allows us to vary the resistance. For example, in this circular rheostat, as you turn the knob, which is on the other side of this object, it turns this bar here, and this is all wire. And so by increasing the amount of wire or decreasing the amount of wire that the circuit has to go through, you vary the resistance. Here's another variable resistor, and you can connect your circuit coming in one end and coming out there, or there, or there, or all the way at the end, but these are all turns of wire. And the more turns of wire the electricity has to go through, the greater the resistance. This enables you to vary the resistance. For example, to dim the dining room lights and create more of an atmosphere. These resistors are not variable. They are constant. Now, one good example, important example, of a non-ohmic material is called a diode. It is a semi-conducting device. And of course, if you look at that word and break it down, basically it means sometimes it conducts well, ohmically, we could say, and sometimes it doesn't. One of the ways that you can alter the ease with which it conducts electricity is by using different kinds of materials that are non-metallic, or by varying their temperature. Sometimes they will not be good conductors at high temperatures, but they will be good conductors at low temperatures. One of the principal reasons to use a diode in a circuit is it's like a one-way valve. If you think of alternating current, hopefully you've heard of that before, alternating current goes back and forth, at least in the United States, 60 times a second, by virtue of the way in which it's generated back at the power plant. We'll get to that in a later chapter. So it alternates positive, negative, positive, negative. So a diode would allow you to only let the current go in one direction and prevent the current from going back in the opposite direction. You would use a diode in those electronic devices like computers and so forth that only need trickles or small amounts of direct current electricity. Way back at the beginning of the 20th century, there was a dialogue between Tesla and Edison, Thomas Edison, over whether our electricity should be primarily direct current or alternating current. And that's an interesting bit of history, which you can look at and look up. And there's also a cool movie that has to do with that whole relationship as well. There are also electronic devices called transistors, which are nonlinear, meaning they are non-ohmic as well. If you go into electricity or electrical engineering, you'll learn a lot more about them. So this graph here shows the linear relationship. With zero voltage, you're going to have zero current. And this would be a non-ohmic right here, non-ohmic, because it's nonlinear. It conducts, the amount of current will change as the voltage changes because of the kind of material it's made out of and what the temperature might be. Now, this next phenomenon is called resistivity. And by resistivity, we need to consider the fact that not all metals are identical in the way in which electricity is able to go through them. We do a lab on resistivity. You may or may not have already done that lab. It's kind of like a force of internal friction. And some metals are much better conductors than other metals, which means that that internal force of friction is less. So if we come over here and consider what kind of factors would affect the amount of resistance in a given piece of wire, certainly the longer the wire is, the more resistance you would expect, because it would add up over the centimeters or meters of wire. Cross-sectional area would be like a pipe or a hose. If you have a big diameter, it's a lot easier for the water to go through than a small diameter, and the same is true for current going through a wire. The third factor, resistivity, another use of the Greek letter R or rho, is this variable, this term incorporates both the proportionality constant as well as the unique characteristics of the particular material that the conductor is made out of. Later on, in just a few minutes, we'll talk about the effect of temperature on all of this. So if you look at this chart, you can see that by far and away most of our wires are copper. Back in the 70s, when copper was really, really expensive, a lot of houses used aluminum wire. And I've lived in a house with aluminum wire, and every time I wanted to put in a new switch or an extra outlet or wire something in another place, I would use copper wire. But if you had a copper aluminum junction, it would generate heat, and that's not good. And so I would have to use a special kind of material, which I don't know how I knew about it, but I'd use that material. It's a black goo that would help to absorb and shed any of that excess heat in a juncture between copper and aluminum. Now, obviously, silver would be a better conductor to use in the sense of less resistance because its resistivity is lower. But of course, silver would be inordinately expensive and not practical to use unless you wanted to put it into a circuit that was extremely important and a circuit that you really, really wanted to avoid any kind of oxidation at all. And of course, silver is much more inert than is copper. Now, notice that all of these resistivities are given as 10 to the minus 8th power for the purpose of comparison. Now, nichrome wire has a super high resistivity, which means that when current is plowing through a nichrome wire, you're going to get a lot of heat. And you would use nichrome wire when you want the heat, like in one of those electric space heaters or in a toaster, because you want the heat in order to make toast, obviously, or to generate heat to warm up a room. Here you have some materials that are not metals. These would be semiconductors, carbon, germanium, silicon. And then you've got some non-conductors down here. This idea, this phenomenon of temperature coefficient of resistivity and the unusual feature that some of them are negative is picked up in just a few minutes. And here's a discussion of some of the old-fashioned, though most people still have some, light bulbs. The kind that have a tungsten filament. Thomas Edison tried probably literally about 1,000 different materials before he found tungsten as something that produced a lot of light and lasted for a long time. But it's interesting to read about this, even though these light bulbs are rather rapidly being replaced by LED lighting. Now, if we do a math problem, and we begin with the equation for resistivity, our goal here is to calculate the resistance per unit length of a 22 gauge nichrome wire. Now you can go online and find the diameter of 22 gauge. 20 gauge is a measure of thickness. And interestingly enough, and weird enough, the bigger the number, the skinnier the wire. So 22 gauge would be much skinnier or thinner, smaller diameter, than say 10 or 12 gauge. Typically, the normal wire that you use in a house is maybe 12 gauge. If you need a slightly thicker wire, you might use 10 gauge. I've on occasion used 14 gauge if all I was doing was wiring in an electrical switch that didn't need a lot of current. But this is generally the code right there, 12 gauge. In any case, that's how you're going to find your cross-sectional area in case it's not given to you. In this case, they give you another related fact, and that would be the radius of 0.321 millimeters. So right off the bat, you know you're going to have to do a conversion from millimeters to meters, and you're going to be cross-sectional area is going to have to be in meters squared. So that's the first thing we do right here, is we find our cross-sectional area because we're going to need it in our formula. Then we can rearrange this formula, and it's rearranged right here, to find the resistance per unit length, which is what the problem is asking for. We're looking for R over L. And so we need to find our resistivity, which comes from the chart, or you would be given it in a problem, and your cross-sectional area, which you just calculated, and now you find the resistance per meter, 4.6 ohms. Then you can apply Ohm's law to find the current that's going to be going through that wire with that resistance if it is under a 10-volt potential difference. And by the way, you're going to be using Ohm's law hundreds of times, with no exaggeration, over the next couple of chapters. Over here, they talk about oxidation, which you might remember is a chemical process, which is going to produce a metallic oxide on the surface of the metal, thereby increasing its resistance. Now, temperature variation of resistance. If you look at this old-fashioned light bulb, and it's really old-fashioned because not only does it have a filament inside, which is that curly Q wire that my arrow is pointing to, it also is clear glass instead of a glass that has a coating of phosphor on the inside to give more of a warmer glow rather than a harsh light. But that's the filament we're talking about that the electricity has to go through. And there is a temperature variation that affects the resistance, or we could say that the resistance is affected by temperature. And the way we calculate that is this value right here is the resistivity from the chart. It is the theoretical ideal, so to speak, resistivity. This is the actual resistivity as a result of taking into consideration temperature. And so T minus T sub aught is your change in temperature. This is the temperature of all the resistivities in the chart, 25 degrees Celsius. It's 20 degrees Celsius. Usually in chemistry and in physics, we often use 25 degrees Celsius as our standard temperature. So this is about the upper 60s in Fahrenheit. And this alpha here is the temperature coefficient of resistivity. And again, you're going to be given that on a test, or maybe you're given enough information to solve for alpha, or you'll be given a chart where you can look it up. So basically what I'm saying here then is that this term right here is the adjustment we make to the theoretical ideal resistivity to find the actual resistivity as a result of whatever this temperature has to be that is different from 20 degrees Celsius. And then you have a math problem that's not too difficult to do using this information. So here we're talking about platinum, and here we're talking about a 50 ohm resistance at 20 degrees. Another part of the problem, we're going to talk about 76.8 ohms. And so if we come over here to look at the problem, the first thing we need to do is find our delta T, change in temperature, and that's going to go in there. We have to look up that resistivity that's affected by temperature, the temperature coefficient. Here is the actual resistance. This is a variation of that formula we looked at just a minute ago, where the length cancels out because it's the same. Cross-sectional area cancels out because it's the same. The resistivity cancels out because it's the same. And we're actually looking at the net resistance. And so this is the resistance of the melting point, but this is going to be the new resistance. And we're going to stop right there. And the last screencast on this chapter will talk about electrical energy and power.